So we've calculated the electric field of a simple charged rod, a little one-dimensional length of charge. And we calculated the field on the end and then off to the side. And those problems get harder when you get into different shapes of charge. And when you get into different shapes and curved surfaces, you have to really be careful what coordinate system you use. So let's do continuous charge in more dimensions and coordinates. So here I'm going to show you how to start, where you find the dq for different kinds of problems, and then we'll do one. So first of all, you can have more than one kind of charge density. So we already did linear charge density, which we write as lambda, and that's charge per unit length. That's linear, so that's in coulombs per meter. That's how we did the rod. We gave it a certain charge per unit length. You can also, though, have a surface charge density. And that's what you might expect. Its symbol is sigma, and it's just the amount of charge per meter squared, the amount of charge per unit area. But how you do problems with lambda and sigma kind of depends on the problem. So one way is to go with Cartesian coordinates, which is just a fancy name for the standard xy coordinates. So if we're going to do a linear problem in Cartesian coordinates, then you really just need one coordinate. You just need x. And it's just like before. We put it on the x-axis. We put plus x that way and minus x that way. We put the origin in the middle. But the key was this line of charge had a charge density lambda, and we just said dq is, when we had to treat this as a little individual charges, we had a little length dx, so dq was just lambda dx. And we set up the integral from there. So now, let's see, what if we were faced with a surface charge? We might be given a square with charge density sigma. Well, if you're going to treat a square in Cartesian coordinates, which of course is the way to do it, is you might say we'll put one side on the y-axis and one side on the x-axis like that. And then you still need a differential element. Well, now in 2 dimensions, the differential element is a differential area. Okay? So in this case, the area would also be a little square like that. And its size is based on a little differential dx in the x-axis, this is getting small, and a little dy in the y-axis like that. Okay? So we would just divide this up into a little differential area. So then the dq, in this case, it's sigma times dA. Same basic idea, you just take the charge density times the area dA. But now we want to translate dA into the actual coordinate system. So we say dq is sigma times dx dy. Because our little dA is just a little square, or a rectangle, where one side is dx, one side is dy, so the area is just dx dy. Okay? So in Cartesian, that's how you would set it up. You may also want to use, for some problems, polar coordinates. So these are usually given r theta. Okay? And you can have problems that are still 1D charge, linear charge density, but in polar coordinates. And the example is this. If you have essentially a line of charge or a thin rod of charge that's bent into a semicircle, so say it comes down like that, and then this also goes around like that. And you're still just given lambda. It's still lambda equals the total charge on this rod divided by the length, which in this case would be half of the circumference of the circle. So this you would also treat in polar coordinates. And what you would do is figure out where to put everything. You'd put the origin here. And the way polar coordinates work is you have some angle you kind of define as 0, so it could be straight up. And then when you go to a point in space, you define it by how far you went out in terms of the radius. I've got to distinguish my r's and my sigmas here. How far you went out in terms of the radius and how far you went from angle 0, and you call that theta. So it's r and theta is how you define this thing. Okay? Now, we have to get to a differential element. So a differential element is a little piece of this thing. So just like we had a piece of the linear charge here, dx, here we need this little piece. And in the end, dq is lambda times the length of that piece. Now in polar coordinates, the length of that piece is r times how much you changed theta. Right? So when you're going along this curve, r doesn't change. So it's r d theta. R d theta is a length. Theta doesn't really have units, r has units of length. So that's your dq if you're doing a linear charge density on a curved surface. Now, what about a surface charge density on a curved surface? Or in this case, we would do a round surface. So I'm out of room here. So let me do it here. Okay? So the curved surface you would probably deal with is a disk. Let's imagine we have a disk of charge. It's kind of perpendicular to the board is how I'm trying to draw it here. And it has an origin, and it has some charge density, sigma. Okay? And you have to calculate the electric field somewhere. Doesn't matter where. What we have to do is break it into a differential area, just like we did that square. So dq would be sigma, the charge density, times dA. So it's just how do you draw a dA on this circle? So what you do is you're going to have to vary r and theta. Okay, so let's say you come out here. This is r, and again, this is theta. Okay, so let's pick a little differential area. What you have to do is you have to come out to a certain r and stop, and then go a little bit farther. This is r, and then this is r plus dr. You've moved a little dr right there. And then you sweep that through a little angle, and you do it again. R and r plus dr. So this is dr, and here you've gone d theta right in there. And then you know this little length is r d theta. That's the length of an arc. Whoops, the length of an arc like that. So if you want the area, you think of it as a little square, and the area is just r d theta times dr. So dq is sigma times that area. R d theta is this length, dr is that length, but we often rearrange it so it sounds nicer. R dr d theta. But really what's making the area is r times d theta is one side, dr is the other side. Okay? And when you write this, you got to be very careful that your r's and your sigmas can be distinguished. The way I normally write, they look similar. So I got to be careful when you're doing these kinds of problems that you don't mix them up. Okay? So we can keep going here, and now what we can think about doing is a problem where we actually calculate the electric field. But I see we have a question first, so let's go back before we keep going and see what this question is, and it is KT anomaly. What about 3D? Yes, of course, you can have 3D. So we would call that a volume charge density. So let's just add it to our table here, volume. And in that case, we call it rho, and it would be in coulombs per meter cubed. So charge per unit volume. If we wanted to define a volume element, we have to pick a coordinate system. If you wanted to continue in Cartesian coordinates, you would just add another dimension. So dq, your charge element, would be the density, rho, times the little volume dv, which is just in Cartesian dx, dy, dz. If you think in terms of the angular coordinate systems, you have, in 2D we had cylindrical. So if you want to take that to 3D, all you have to do is add a z-axis to it. If we look at our circle here, our polar coordinate system, if we just add z, then you can imagine this little area we talked about before and just have it come out in dz. So in that case, we could do this in what would be cylindrical coordinates. dq would be rho times r dr d theta, dr, r dr d theta, that's the area, and then we just add dz. And that would turn it into a volume. One more option you have for 3D would be spherical coordinates. Those are more difficult. There you have a radius dimension or a radius axis and then 2 angles. It gets very confusing. So most problems we do, we're going to stick with area, charge per unit area. We might do some volume, but if we do, it'll definitely be one of these 2 coordinate systems. We won't do spherical. So let's go ahead and do a problem just in 2D.